All right, can everybody hear me? You can answer in the chat if you want.
Yes, we hear you, sir.
Very good, very good. Thank you. Good. All right, so I guess without further ado, and people see the screen share here, it says storage systems, storage for database systems. I'm assuming?
Yep, works fine.
Okay, let me just verify that this is being, okay, one sec. I just want to absolutely verify that this is being recorded, because it looks like we don't have, well, we have, okay, the number of participants is coming up, so, okay. But I got the feeling that some people are going to be watching this as a recording. So, okay, yeah, it looks like it's recording, so that's good. Share screen again, and share. Okay, so today we're going to be covering kind of more the physical and the storage and the kind of physical aspects of database storage, I guess is what I'll put it. The first thing we'll start with is we'll just talk about the actual hardware and like that environment. And then we'll go into some of the common structures that back databases. But before I start, are there any questions about anything that I should address at this point? Okay, so we're gonna just do kind of a classic lecture today. But interrupt me in the chat session if you have any questions, or even just voice them. All right, so here we are. Okay. So let's just get this going here. Okay, very good. All right, so yeah, so the first thing just to kind of note is the obvious, and that is that we're talking about bits and bytes here. So a lot of times in the notation, you'll see a small b will denote a bit, where the capital B will denote a byte. And we have, I guess most of you have heard of kilo, mega, giga, and tera, and then peta, probably a lot of people have heard of peta. But then if you want to even go further, there's exa, zeta, and iota. So I'm not really sure what some of these are going to not ever be achieved by humanity because it just gets so large that it becomes like the number of atoms in the solar system or something. So at that point, you know, good luck representing that, having that much storage. Anyways, just in the notation, a lot of times you'll see when people are talking about these sizes, you'll see K, usually K is lowercase for some reason, for 1,000, M for mega for 1,000,000, G for giga for 1,000,000,000, and T for tera or trillion. Okay, so there's two meanings of this, of course, and that is that one is just the kind of the decimal meaning, which means that like 1 KB could mean 1,000, which is kind of the normal base 10 way that we think of things. Then the question, of course, is, well, 1 MI. And so when you see the little I there, then they're talking more specifically about the binary size. So the binary sizes are always a little bit bigger. So we basically have, 1,024 is in 2 to the 10th, right? So that would be KIB. Would mean that, but it doesn't really matter because usually you're just talking you're trying to kind of ballpark things anyway. So usually you skip the little I. So you're going to use just kind of have the base 10 intuition. Okay, quick. So this is something that I guess, I would expect. This is a good. All right. So this is something that is a trick, you'd say, but it's something that you should all know. It's maybe your generation isn't so quick, which is like head calculations. You're more kind of do stuff on the calculator, but at least get this down. If I say, what's 2 to the 35th? So what's 2 raised to the 35? That's like 35 bits. So what are the possible number of values in 2 to the, in 35 bits, basically. All right, well, you can break that down. It's 2 to the 5th, and then it's times 2 to the 30th, right? Based on that simple rule. So that means it's 32. So really, now, honestly, if I ask you guys, well, hey, what's 2 to the? I'd say like, what's 2 to the 7th? Quick. Oh no! See the kids here. Alex, name. Papa before last I know. He had the sniffles, so he has to stay home because of the COVID. He had the sniffles on Sunday, and he still has to stay home. But it's okay. He doesn't have a fever. Hey, Alex, snälla, kan du gå till andra rummet, snälla? Okay. Sorry, I need to. This is kind of pause. I need to. All right. Sorry, I'll be back in one second. This hopefully this will pay off. Come on, Alex. Come. All right, puppy. Really? Fångar det. Här. Oh no. Okay, there you go. Apologies. I'll edit that out of the the recording. All right. So like quick, what's 2 to the 7th, right? Okay, so 2 to the 7th. All right. Well, it's 128, right? What's 2 to the 6th? 64. Okay, so the thing is that you should memorize all those up to 2 to the 10th is 1024, right? 512 is 2 to the 9th. Okay, so you really got to have those memorized. I would suggest. But if you have it memorized, then it's very quick to kind of just do these kind of calculations. But anyways, I would just recommend doing that. I think sometimes it's an interview question. Somebody might just ask, what's 2 to the 7th? And if the person kind of pauses, they don't get the job. Because if you're a computer scientist, you should know at least know your base 2s up to 10. My God. Okay. So, all right. So a lot of times also, this is just kind of a rule of thumb here. That is that when you deal with data transfer, because of the encoding, extra encoding possibilities, you basically will consider it to be 10 bits per not 8 bits per byte. It's just kind of okay. So this is all, I think that you guys have all seen this before. So yeah, so an example thing is a SATA 2 interface with speed of 3 gigabits per second can transfer 300 megabytes per second. That would be the calculation. All right, so then there's the memory hierarchy. So we talked a little bit about this last time during recitation. I just kind of alluded to how we were going to discuss this. Right, just checking the chat there. So the memory hierarchy is just kind of, you basically have increasing size and decreasing cost per unit of storage and increasing speed at the top. So a static RAM, so basically the RAM that's inside the registers inside the CPU. So the CPU cache of memory. That's the fastest, but it's the most expensive. And then you have basically main memory, which comes next. And then further down that, as far as just increasing speed and decreasing cost, you have the SSD devices. And the discussion, then you have after that, you have hard drives. You have mechanical disks or magnetic disks that have moving parts, rotating, spinning platters. Optical disk, I mean, that's kind of a little bit of an exception there, but then at the very end, you have the magnetic tape. Okay, so that's the cheapest per unit of storage, but it's the slowest to get. This is kind of a natural system. So if it turns out that anything tries to violate this kind of structure, it will be excluded from the market. So the market will just, so for instance, if there was some kind of radical development in SSDs, so they actually became cheaper than magnetic disks, then the disks are out. It's over. Okay, so there's not, and these things have to kind of justify themselves. So so this memory hierarchy is just a natural outcome of the market, and a natural outcome of just the various trade-offs. So each of these technologies is then valid because it sits somewhere on the hierarchy. Okay. So optical storage is a little bit exceptional because it's got a, I mean, there are some advantages. There's some reason why people continue to use these, but maybe it's more legacy at this point. All right, so for databases though, the central consideration is the way things are modeled and the way things are kind of thought about is mostly between main memory and the disk. So those are the kind of the two levels that we're going to look at. We'll talk a little bit about SSDs, but even the distinction between the main memory and SSDs, that's in some sense that's going to, well, it's still open research. It's still research issue or area where they're trying to kind of refigure a lot of the algorithms to adapt to SSDs rather than magnetic disks. But basically, we're going to base our stuff on what we analyze on this distinction between a main memory, which is volatile, right? Main memory, you can lose it if the power goes off, and the disk, which is or the SSD, which is non-volatile. So once you store stuff to it, then if the power goes off, it's still there. But these are slower. The degree to which magnetic SSDs are faster than disks, they're significantly faster, but they're still not as fast as main memory. So you have a main memory which is volatile and very fast, and then you have a non-volatile and slower medium to store data or to access data from. So this is the main juggling those concerns is the main thing the databases do. Okay, so main memory databases. Okay, so sometimes what you say is, why don't we just take to kind of really to reduce the IOPS to the storage device? Why don't we just put everything in main memory? And a lot of databases actually do that. They in fact do that. A lot of them in the financial industry, where it's like the high frequency trading guys, a lot of them have just these giant main memory databases because what's most important is to do things quickly, and it's not so important that that you save things off. I mean, you're not really making that many updates. You're more doing very quick reads. So there are certain cases where you do use pure main memory databases. You can actually, unfortunately, you can't do this really with PostgreSQL. I mean, unless maybe you set up a RAM disk in a certain way, or there may be ways to kind of fudge it. But with MySQL and SQLite, especially SQLite, has a really nice way that you can kind of make things automatically run in memory. The thing is, though, is if you have something that's heavily updated, and you want to be able to do transactions and make sure that they're durable. So once you do the transaction and it commits, you want to make sure that it's actually written to something that's non-volatile, because maybe the power goes off. Then you're still going to be doing a lot of write-outs. So that will cause IOPS to writes to the disk or to the SSD. Okay. Also, I mean, the thing is that with main memory, I mean, depends. I mean, it's kind of hard sometimes to come up. I mean, basically, I would say with databases, like you have basically either the databases are actually pretty small. I mean, relative to main memory. So a lot of databases that are like a web storefront or something that is put in a database. I mean, it's not going to be that big, so it's always going to be able to kind of fit into main memory. But if you talk about some database like Skatteverket's full record of everybody's filings for last year, that's not going to fit in main memory, right? So you have these giant databases that are it's going to never fit in main memory, or you have these databases that they feel kind of big, but actually you can stick them in main memory. So I think a lot of databases people work with actually are pretty small when we look. They didn't used to be, like 20 years ago, they weren't small, because back then, oh my God, having like the Music Brains database that seems so giant, and you can't stick it in main memory. But now I think you can. I mean, essentially. So, right. Okay. So, so there's main memory, just trying to put everything in main memory, and then there's solid state devices. I want to talk about this a little bit. Okay, so these are becoming less expensive. So I did a little bit of looking into this. So will they replace mechanical hard drives? Yeah, I imagine they will in the future. SSDs are they're much faster, they're lighter, right? So so any kind of, you don't have to carry around these bulky machines, these disks, these things with spinning parts. They're more durable and they use less energy. So the only thing they aren't is less expensive. That's the main issue. Okay, so I guess they currently looks like the commercial ones can get to about 4 terabytes. So that's not a trivial amount. I mean, how many database? I mean, if you think about database size here, I mean, how many databases can fit in 4 terabytes? Oh my God, that's a big database. All right, the cost per gigabyte is still about 10 times that of a spinning disk. So there's a cost issue. There's also a lot of different. They've got some different properties. Now, I haven't looked into it so much, but especially with writes, I'm not really sure if anybody's had any experience with this. Oh, good. So I got some people making some things. Okay, good. Yeah. But it's private. No, you guys can't see that. So people have a lot of expertise with it. I mean, a lot of people have looked into a lot of this stuff. So it's nice if, yeah, there's lots of different technologies out there. So, the issue of I don't have much experience with this, but I guess there is there's a limit to how much you can write to an SSD. I don't know. I've never reached. At least I hope I haven't. But if you write, you write. If you do too many writes, I guess in the limit you exhaust the medium. I'm not really. I don't know much about that. If anybody knows anything about if anybody's ever exhausted their SSD with too many writes, please put a comment in the chat. I'm just waiting. Maybe I'll get the error like later today, because I've done a lot of writing to this SSD, so I don't know. But anyways, yeah. So there's still a lot of research that has to be done in development to kind of integrate them deeper into databases, optimized implementations of over SSDs. All right, so based on that, a lot of the work is going to assume kind of hard drives. So hard drives, like I said before, I keep on mentioning that they're mechanical. So so you just get a kind of a feel for it. It's about 1,000 to 10,000 times for random access. So you're just going to look for, you want to locate one. And then when we talk about getting stuff from storage, the SSDs or disks, when we talk about that in database context, we talk about blocks. All right, so there's going to be a block, and that block is it's probably going to contain more than one. It's going to probably contain like maybe 15 records of a table. All right, that's a block. All right, so everything's organized in terms of blocks. You grab the block and you bring the block into main memory. When you bring it into main memory, technically it becomes a page, or the page. It's some integer multiple of the block size or something. But let's not forget about pages. Let's think in terms of blocks that are in memory. Okay. So if you're just going to you have a giant database and you're going to locate one file. You're going to locate one record and it sits in one particular block, and you will randomly access that block. You figure out some way to find that, and you randomly access it. Then if it's already in memory, if that block is already in memory, if that's cost unit 1, then it's going to be typically 1,000 or 10,000 times more to just kind of go out to disk and get it, because there's lots that involve in doing that. If you talk about continuous throughput, so we're going to read the whole table. So we're going to read a consecutive set of blocks. Then it's about, RAM is typically about 100 times faster. Okay, because you get a lot of advantages when things are continuous on disk, because you just set the only thing the disk has to do for the most part is to put itself in the right spot, and then be moving the head as it rotates and just suck up all those blocks, right? So the amount of cost per block, it's not as expensive as random access. All right, so yeah, so we're going to go through this very quickly. I think that probably a lot of you have seen this, but it just gives you some sense of really what's going on physically in these things. And someday we won't even have to look at this anymore. So a disk is basically consists of basically a set of platters which have this substance on it, which can get a 0 or 1 kind of signaled onto it. And then you have a track which is like on one particular surface. You have the platter, then you have the surface, then you have, so usually a platter will have up and a bottom surface. So there's 2 surfaces here on one platter. And then you have this read-write head here that's going to swoop over the thing as it's rotating. So this whole thing is rotating here. And then on one particular track, on one track on the surface of a platter, you'll find a sector, and that sector usually corresponds to a block size. All right, so it just has to kind of wait for that, and then that's going to be like maybe on the order of like 2K to 5, to 5K or something. It could be, it's configurable. All right, the whole thing itself here defines a cylinder. So a lot of times you'll find that, well, these can all go in parallel here. So through one cylinder, if you store the whole file on several cylinders over all these platters, then you can suck it up all very quickly, because you can parallel read off of the read-write head. So the thing is, this thing's rotating, this whole thing is rotating, and this thing is moving back and forth, going to different cylinders, right, where it can suck up or write down the data. All right, okay, so that's just saying that over again. All right, so these are just these are kind of just some measurements about what we get. So number of platters is rarely more than 4. So if you look into these things. The problem is these things are spinning, and sometimes you have a head crash. Okay, so that assembly will crash into the medium and kind of just destroy things. So that is the durability problem with disks. All right. Okay. So yeah, 512 bytes. Okay, to 2K bytes is a standard for a sector size. Okay. Yeah. So these are kind of this what we get. All right. So there's two aspects then when you're going to go out and do a random access. So let's say there's one sector which corresponds to a block, And we basically have some table that tells us, okay, we want to bring that sector or that block into main memory. Well, what we got to do is we got to do a seek time, which is the amount of time it takes to position the read-write heads over over the cylinder that has a that has a surface that has a sector that is that block, and then we got to wait for it to rotate around so it can read it. Right. So that basically these are going to be in the order of milliseconds rather than nanoseconds. Okay. So this is the reason why we're getting 3 to 4. Orders of magnitude worse performance, because we got to wait for this physical stuff to get done, right? Which we don't have in SSDs. All right. So also another thing also just to say is that just it's kind of an obvious point, and that is that Moore's law is not applying to the speed at which disks rotate, right? So the rotation speed of a disk is not speeding up because there's some physical limits there, nor is the speed at which the read-write head goes back and forth. I mean, those are just kind of things that have physical limitations. So, so that's why it's really not getting any better. All right. So the key issues then are the 3 key measurements are basically you're talking about like disk to buffer. So that basically you have the disk once it goes into rotational latency, it goes into the seek and then waits for rotational latency, and it's actually bringing in the data. Then you have the time it takes to how much can you transfer to a buffer. So the buffer is some memory unit on an actual hard drive, and then how long does it take to take the buffer into memory? And these are all going to be a lot quicker, of course, and we have pretty good throughput here. But these are measurements that you'll see kind of specced out. The random time access is the total time to fetch one data block and send it to memory. Okay, so again, these are, 3 to 4 orders of magnitude higher than just looking if it's already in memory. All right, okay. So the primary physical factors are the seek time, rotational latency. Those are the big ones. Okay. All right, so hard disk access and databases. Sometimes you can so it's you can try to kind of there's a lot of work that goes on in this and trying to kind of organize things so that you get really good database performance, but you can't. I mean, it's kind of black magic to kind of get this done right, and there's a lot of it'll come up in a second. There's a lot of issues that make this harder. Then there's also the issue of reliability, which has to do with RAID. So I'm actually not going to cover RAID because I don't think we want to go into this stuff so much. Most of the time, you just kind of rely on the cloud provider to kind of to do this for you, essentially. Okay. So yeah, I mean, this IOPS or the IO operations, this is what you want to minimize. I mean, you want to make, most of the time what you want to do is you want to bring stuff into memory, work with it there, and then try to minimize the number of IOPS. If you tune it, then you basically, the issue is basically what you're going to do is you're going to keep in memory what's likely to be needed again. So I mean, the size of memory that the database is taking up when it's up and running is quite large. So you have a lot of blocks to work with there. So you want to bring things in. So you try to predict what's going to be coming in, and when we get into indexing, you'll see that a lot of times what you'll do is you'll have the index definitely in main memory, so that you'll minimize the number of times you have to go out to disk. There's some other, there are things that are kind of tugging at the performance issues, and that is that there's a memory processor speed mismatch. So basically what we have here is that the processing speed is increasing much more rapidly than the memory speed. So things really, I mean, what we're basically going to wind up doing is ultimately things are going to move into the processor. So these memory units on the processor are going to then correspond to, quote, main memory in the future, and main memory is going to correspond to disk access. So it's always going to be this thing where you have this faster memory, but it's limited, and then you have this slower memory that's that you have to access because, well, it's larger, so you can actually store everything there, but then you have to be intelligent about how you access that and bring it into where you can actually work on it very quickly. Okay. Yeah, so database tuning. So a lot of database tuning, yeah, it's become paramount. Oracle, I know, is invested a lot in trying to get AI to do this stuff, to make this more of an optimization problem that AI can figure out. But maybe not. It's just there's a lot to consider in terms of. I mean, there's so many different factors. It's hard to kind of turn it into a giant optimization problem. So if you can do it, then you demand. I mean, it finds you get rewarded in the market for being able to do this well. Because everybody wants faster databases. All right. So this is kind of an interesting issue that that you need to kind of consider. That is that I mean, you have basically two choices here. You have like so some people would say like, well, what is Oracle really good for? You know, it's like, so Oracle is one thing that they can do is that, so when Oracle bypasses the operating system and works directly on the disk itself. So when you buy these Oracle machines, so there's these really expensive machines that have Oracle installed on them, and they essentially have an Oracle type operating system on them, because what they do is they basically have fully taken control of the disks and fully taken control of the hardware, and everything's based on, you know, the database model, as opposed to these open source systems like we have. So this open source systems that we're using, basically they're portable, right? It's a portable, you know, it goes over multiple different types of hardware, and they're simple to implement, and they're portable, but yeah, I mean, physical disk. Yeah, but what we'll see is we have this double buffering problem. So the double buffering problem is kind of the critical thing that happens in these open source or these portable systems. So the data is transferred twice, once between the disk and the operating system. So the operating system slices out a big piece of memory, and then between the operating system and the database manager. So if you have, it's possible that things get duplicated along that path, and that's pretty bad if you have a lot of data, right? Somewhere like these commercial databases, which really do a low level, have a really low level interface, OS-based interface, they can really kind of get down there and really work with things. But even they have a hard time, because it's like sometimes these disk controllers, so I was going to say about that before, is like the disk controllers, sometimes they have their own way of kind of organizing things, and they are going to make their own kind of, you know, strategy, and it's hard to kind of get in to actually get kind of, unless you're really going to go native on them, it's hard to kind of get in there and really get control to turn it into a database, to really get control over where the blocks are, all that stuff about the sectors. Anyways, that gives you an idea of kind of how things, this gives you an idea of kind of some of the structure, okay, so I have a question here. All right, yeah, so it's something about MongoDB and Oracle. That's kind of, both of them are basically confronting these same kind of issues. I mean, the issue of MongoDB versus an Oracle, that comes at a higher level. That has to do with kind of with how they represent things. MongoDB is one of these, essentially has a data structure that looks like JSON. It's not a relational database. Oracle is a relational database. Oracle, just think about Oracle as PostgreSQL, like that kind of level of functionality and more. But then really commercialized and really like delivered in a hardware package, so that a bank can put Oracle in the corner and have everything kind of work, basically just work, and work very, very efficiently, and also has a lot more support for like distributed databases. Actually, like DB2 is another one. That's IBM's product. I mean, they're really good with distributed databases. So for like big banks and stuff, I mean, this kind of stuff. So, you know, it's one of those things where the guy down at the gal down at the bank, they don't want to, you know, they go to their bank manager and say, we could save so much money if we just went with PostgreSQL and not pay these Oracle fees. But it's kind of like, the banks can say that. I mean, compared to our cost structure, this is worth it because we want the security. Okay, so Oracle, and then Mongo. The bank's not going to use Mongo, I don't think. But anyways, okay. So, anyways, but this is just kind of looking at the physical kind of stuff. Okay, so let's bring up here now. I'm going to bring up another. Just keep on going here. All right. Right. Okay, ocular. And then we said 04. Okay. All right, view presentation. Okay, I guess you guys can see that, I'm assuming. If you can't see this, then you'll say something, but yeah, it looks like it would be there. All right, so let's go on now. Let's get more database oriented. So we have like a disk, or we have an SSD or something. We have essentially we just have this issue that we have a slow and cheap non-volatile memory, and we have a fast but volatile memory, and we want to bring things in intelligently as we do as we search database. All right, so the first thing is to just always consider that is that this issue of data independence. All right, so data independence is basically the functionality. So strictly speaking, this stuff that we're going to be covering today should be invisible to most users. I mean, you write at your SQL, you access the database. You don't know how it's being stored on the disk. You don't really, a lot of times you don't really care. I mean, it doesn't really matter that much to you. It's like, well, let the system decide how it wants to organize stuff. The view I have is of a set of tables which I access via SQL, and there could be a radically different physical way in which they're doing it, but it would look the same to me. Maybe it would be slight performance changes, but it'd be the same to me. So that's basically this notion of this data independence. That is that from your external point of view, from SQL or something, it's irrelevant what the internal storage is. It's just, okay, they pick some way of doing it. It's encapsulated, right? Relational models exhibit this by design. Not all systems did that in the beginning of databases, but now it's kind of a requirement now that you have a language, you have a way in which things get expressed, and you're not going into these really low level, you're not doing these low level decisions. But still, if you're really talking about like you're responsible for the database, it might be kind of nice to know and to get some control over how things are being done at the physical level, because it affects performance. All right, so the first thing that we need to consider are what are the different kind of access, the different types of access we're going to get to data. And there's really basically only three of these. There's key-based support, which basically is retrieval of data based on the values of specific keys. And this suggests an index strategy, but just think of it like saying, I have this giant database, I'm Scott de Werket, and I want to, for this particular persona number, I want to bring up their record. All right, that's a key-based access where I just want one of them. I'm going to bring it up and bring it in. Okay, so that's key-based access. So then there's sequential processing. So for instance, a sequential processing, it's retrieving large amounts of information in some order that suggests that the data themselves should be stored in the appropriate order. Okay, well, sequential processing, here's an example. Sequential processing might be like, well, give me the order of all the people in Sweden ordered by persona number. So I want to get the list kind of printed out in that order. Now that seems a little bit contrived, but that's the pure case of sequential processing. Probably a more practical example would be something where I want to go through everybody in, say, Umio, where I want to go through everybody. I'm going to say, let's just take a pure case of sequential processing. I want to go through every person in Scott de Werket's database, and I want to get an average income for the whole set. So I have to look at every tuple. So I have to sweep through the full file. I have to sweep through the full file, and I keep some kind of running tally about what's the total divided by the number of people I've seen so far. And then at the end of it, I can then just calculate what the average salary is, or other statistics for that matter. Okay, so that's an idea of sequential processing. And then something that kind of brings them together a little bit is a range query. So the range query would be certain parameters falling within a certain range. So a pure example based on this would be persona numbers between one particular value and another value, and kind of get everything in that range. Okay, so what we'll see later, just as a kind of just something as a foreshadow here, is that what you'll find that these indexing strategies, these kind of classic indexing strategies, like what's called a B+ tree, these trees those are good at both key-based and also range queries. But a hash index or hash strategies are not good at range queries because, well, things that are very close might wind up being very far away in the hash because the hash is kind of a randomly distributes things across the whole space. So we'll find here that, well, in short, we'll find that hashing actually is not really used so much in databases. But okay, but it's not used so much in databases, but we'll come to later on where it is used in databases, but it's not used so much as a kind of indexing strategy on the actual physical data. It's used more as a a lot of hashing is used as to calculate intermediate results when you're doing query processing. Well, we're going to not cover that today. That's going to be covered next time. All right, but just these are the kind of access to keep in mind, and this maybe will become clearer as we go through this. But again, key-based, like a specific key value. Sequential, let's look at the whole set of values and go through them in some order. And then range, let's go over a certain small section of them in a, well, we have a start and bottom to a range, and we do a little bit of sequential processing over that range. Okay. All right, so what I'm going to cover here then is the classic way that databases do this. So they're doing this as a row store. So basically, the way memory gets structured is it's on a per record basis. So you take the first record of the table, then the second record, then the third record, etc. Right? This is opposed to column stores, which is it's a bit more specialized to OLAP, if you recall from the last lecture. Those are column stores are a completely different structure but we're not going to touch those today. We're going to do the classic example of a row store. Okay, so the row-based implementation then it's pretty straightforward. So if we take this example here, where we have this department table with a department name. It's pretty clear what happens here. So this is going to be like 21 bytes when you consider the end, the end signal, 15 bytes for the building, and then the budget is going to be 4 bytes. Okay. So that's what a record is right there. So there we have, so we basically have 41 bytes, right? That's how many bytes a particular record is taking up. Okay, so the physical storage of these records they're in blocks. So a block, like I said before, a block can be like 512K up to 2K, but sometimes you get bigger, like you get up to like 5K or something, but you'll get, the block size is you're going to be static. You're going to configure the block size, or it's just going to be defaulted or whatever it is. So what the block does then, it usually corresponds to a sector on the hard disk or some small multiple of that. Now the blocking factor has to do with the number of records which can be stored in a block. So in that prior example, we had 41 bytes per record, and then let's say we have 512 K, or we have 500, let's say we have 512 bytes per block, then we're only going to be able to stuff what? Like, you can do the calculation roughly. I mean, I don't know, some number. So if it's 15, I don't know, something like that, 14, you can do the calculation. So the thing is that what we always do in this class, and I think in practice also, is basically we don't split records over blocks. So like as we're filling up blocks, right, with records, if it comes down to, there's like 4 bytes left, can we stick 4 bytes of the next record into that and then span it over to the next? No. Just let that be just kind of extra space that's just going to be, give it up, right? We want to have it so that records fit into one and only one block, right? So it simplifies the implementation. Okay. All right. So so how are we going to do this then? So what's the so this right here is just has this. We're going to come back to this in a second, but let's first consider something else here. But so we have this underlying notion that the things are going to get stuffed into blocks. Okay, now when we just think about records, let's go back to and think about just records. So there are basically 3 fundamental ways in which we can store records, right? So let's say I have 100 records of departments coming in. Okay, how am I going to store those? All right, one way is just to do it as a heap, right? So if you recall, like from your beginning programming classes when you did a linked list, that was like a heap. What you do is you just have a pointer. Okay, so you have like a pointer to the beginning of sequence of records, and then you have a pointer to the end of the sequence. Okay, and then maybe you have you have a pointer to the end of the sequence. When you add a new record, you just go to the end of the sequence and you just kind of append it on there, right? You just kind of do the little pointer surgery, and you stick that record on the end, right? If you delete something, you go into the middle of the thing and you take the pointer from the previous and you make that go to the next, so that this one gets, you know, kind of excluded, and then you put that on some, you know, you do some kind of operation where you say free that memory, right? So you're doing a linked list. You have a linked list, which you're just kind of, that's a heap essentially. Okay, that's one way to do things, and you know, the virtue of that is it's really simple. You can also order things on a value. So another way that we could do this is we could have it so that we're going to keep an order on the actual. So as the departments come in, I'm going to keep an order on their the alphabetical order in some kind of structure. I'll keep an alphabetical order on some kind of in the structure. All right. Well, that kind of seems a little more complicated to do, and also when you think about it, it's like, how is this going to work with blocks? Because this could get a little tricky, right? Okay, so yeah, all right. Well, anyways, but that's one way. But assuming there's some way to implement that, to kind of maintain some kind of ordered, some ordering on the records, right? Another way is just is hashing. So hashing is basically you just you have a bunch of buckets kind of lined up somewhere, and then you do a calculation on the record, and then that determines a bucket address, and you toss the record in the bucket. All right, and then based on hashing, then we'll see that later on we'll come to something called extensible hashing, which is actually the way you do this. But that's another fundamental way in which you might organize records. So these are essentially it. I mean, this is, you're going to either order them, you're going to keep on a heap, or you're going to have some kind of hash structure. Those are going to be the ways in which you do this. Yeah, blobs larger than blocks. Okay, that's a special case. That's a good question. So blobs are just going to be, they're going to have their own kind of reserved space. And what you're going to store instead is you're going to store the pointer to that, to a block or a list of chain of blocks, but not blockchain. You're going to have, there's going to be kind of a reserved space that the clobs are going to be in. So the character large objects and the binary large objects are going to be in. But what you're going to be dealing with in the records, though, is then the pointers to those. So so blobs, that was a very good question, but they kind of form an exception to this. All right, so those do span because they get big. Okay. All right. So all right. Sequential organization. Okay, so we're going to look at this kind of order, this ordering here. So sequential. So, all right. So what does it mean for the records to be ordered, disk to be ordered? All right. So here is an example. This comes down to like the way the blocks are structured. So we have a blocking factor here of 3. I mean, it's kind of, these are really small block sizes, of course, but well, this, you get the idea for an example here. So what do we have here? So we basically. So how are these ordered? Okay, so what does it mean for the records to be ordered on disk? All right, so here we have the ordering is on the ID of the instructor relation. So this is for instructors, and we have basically it's the ordering here is 10, starts out with this, and then it goes up to 98, 345. All right, so so inside the blocks, they're ordered, and then we have these blocks are in some type of sequence. Okay, so the way that actually gets dealt with, though, because it's hard to actually have control over exactly how the blocks are being placed. Like the disk controller, it makes its own decisions. So what we do here is we have like next block pointers. So the block also has some extra stuff in it, which basically extra stuff is a pointer. So usually what you'll see is you'll see a front pointer or a pointer that goes to the next one, and you'll see a prior pointer. So you get 2 extra pointers so that you can find out and these addresses here are going to be block addresses. All right, so this is going to be the address of that block. All right, and then inside that block, then the records are going to order inside the block. So through this, you can basically then, if you get the address of this block, you read this guy, this guy, this guy, then you basically follow this block pointer to this block, and then you read this, this, and this. And then by doing that, you can do the sequential processing where everything is going to be done in order. Now, the thing is, it might say, well, what happens if we get a lot of, like in the example before, well, that was with the heap, I guess. But what happens when we start getting a lot of insertions and deletions? So we want to maintain this order, but then we start getting a lot of we get a whole bunch of departments inserted here that have, or sorry, instructors that get inserted here that have a value of like 40114, 400115, 40111. They start stuffing them all in here. Then we have to maintain that structure. So it gets a little complicated in that sense. But we'll see that we have a nice clean way of doing that, in fact. That's something that needs to kind of be maintained. So then, you do all that, and then what you do is, based on all those insertions that came in and the way everything's working with the disk controller and all that, then it turns out that if you actually do a sequential on this thing on the disk, that little head is popping back and forth all over the place, right? So that requires some kind of defragmentation to be run over the files, so that then you can actually go back, do some, just do the work to kind of make these things so they are contiguous on disk, right? To get better performance, right? So that would be an important thing. But that's the idea, though, essentially, is to kind of maintain these blocks. Looks like I have somebody coming.
Sorry, sir, I couldn't understand how these are neighbors.
Well, they're neighbors, like in the case here, they're neighbors logically. Oh, they're neighbors because, I mean, if you see that they're being ordered here on this, the ID of the instructor.
I see. Yeah.
So it's the ordering on that, and then they're neighbors in the sense that they're logical neighbors, because it may be physically on disk. This thing, when you follow this point, this block here may not be next to this block on disk, so it might actually be really a terrible step you have to take here to move the disk controller to get this next block. But once you do the reorganization, then they actually become physically closer on disk, so that you don't have to be moving the head reader around to get this next block. But I think that logically, though, yeah, these are ordered on the ID of the instructor. And this block here looks like that's kind of about, it's a pretty underfilled block there, so that might be something we need to consider. All right, yeah. All right, so I think right now, let's see, what do we have here for time? Okay, we're right now at 11 exactly. Why don't we take like a 10-minute break and be back here well, let's take a 9-minute break. Let's be back at 11:10, and then we'll just continue. But I think we're gonna make pretty good time today. We might actually be able to finish early. We'll see. Okay, I'll stop recording now at least. I think I'll try at least. What? Oh, I see. Stop share. Huh? That sucks. Stop share. There we are. And then. Okay, so I think we can start up again. Yeah, it's 10 after. So yeah, so this is just kind of well, what we're showing here is just kind of how kind of a toy example. So the way this gets solved in practice actually is that what we do is we use indexes. But we do have a file under the hood. So this file, we actually do have a data file, right? So it's important to kind of keep these things straight here. So we have the data file, and this is actually what the data file looks like, all right? It is a sequence of blocks with records inside the blocks, all right? So that's your raw data file. But on top of that, we have an index structure which facilitates key-based access to the file. So, for instance, we can search on this particular ID for 5565. So we can put that into the index, and that will make it so that it'll come right down here into this block, so we can actually pull up that record. Okay, rather than going through all these. I mean, the last thing you want is sequential access, right? You don't want to do a scan of the full file, it's called a table scan, basically. You don't want to search the whole table. When I say give me the instructor with ID 45565, obviously I don't want to actually start here and then just rip through the whole file, right? Just go following down, and that would be dumb. So no way, right? So how do we achieve that? We achieve that via indexing, all right? Now, we have basically some distinctions here on what, these are going to be kind of tree-based indexes, we'll see, a B+ tree to be specific. Basically, we have a classification. Indexes might be classified along these two different dimensions, basically. The first question, are they a primary index or a secondary index? So a primary, or what's called a clustering index, is an index that's built on the actual physical order of the file, right, of the actual data records. So in this case, if we had, nay, Alex, nay, puppy, Papa for last afternoon. I knew that was going to happen. This could get bad. A primary index or a clustering index is based on the attribute that is used to build up, is basically how the records are being ordered in the file. All right. So they could be built. So we'll show a couple of examples here. So the first thing about index, the first question is it primary or secondary? Now a secondary or non-clustering index will be on something that is not, so for instance here, we might actually do an ordering on last names of the instructors, or we might do an ordering on the departments of the instructors. But if you look on the actual disk, well, here's a comp sci here, there's a comp sci there, there's a comp, it's like there's not ordered by comp sci. But we can build what's called a secondary index on actual computer science, right? So that we can, and then hopefully if we use that index, then when we go and we want to just get the people in computer science, we will only get this block, and that block, okay? So it'll be smart about what blocks it brings in, even on a secondary index search. Then there's a question about the actual index itself. So again, remember there's going to be the index and there's the file. This is the file, and we're going to see in a second the index. So the question is the index dense? That is, is every search value represented inside the index? Then it's dense. Is it sparse? That is that no, there are going to be a subset of the values are going to be inside the index. Then it's going to be sparse. So we have primary, secondary, we have dense, and we have sparse. And based on that, actually, you should maybe even be able to figure it out now, and you can put it in the chat here if you can figure it out. But one of these combinations is disallowed. One of these combinations makes no sense. All right, it doesn't happen just by virtue of its definition. So there's basically only three possibilities here of these pairings of primary with dense, primary with sparse, secondary with dense, or secondary with sparse. Secondary with sparse. Anyways, so there's one of those that doesn't make any sense at all, and we'll kind of uncover that. All right, so here's an example here of a sparse clustering index. So it's a primary index. Primary index. So it's an index that's built on the it's on the instructor IDs here. So it's also sparse. That is, and the reason why it's sparse here is because not every value not every legitimate value of the ID is represented inside the index. And notice here, the index here is in green, and the file is well, not in green. So this right here is showing that the file can stay the same, and then we just build the index on top of it, right? Index is like an additional structure that kind of exists on top of an existing file, existing data record, set of records, or sequence of records, sequence of blocks that have records. All right, each link points to the first block containing that index or greater. Okay, so this right here, then, if you're looking for something that's over, over that value there, then you go here. Let's say we're looking for 83,821, then we look at this index and we say, oh, we must follow this over here, and then we go to there, and then we only bring in one block. here is a dense clustering index. Okay, it's clustering, but it's not on the primary key. Okay, so this just shows that this file here now is clustered on the actual department here. All right, so biology and then computer science and electrical engineering, finance. So that's how it's arranged on disk. So you can actually, in SQL, you can control for this. You can say what does it get clustered on inside, when in the actual data file, what does it get clustered on? And then here we have a dense clustering index, because every value here is represented inside the index, so it's dense, and it's clustering. Okay, so it's a dense clustering index, but it's not on the primary key. All right, now we have basically a non-clustering index. So this index here, so if you recall, this was the original file we had where we have the physical order it's clustered on the ID of the instructor. Okay. Now what we see here is that what we wind up doing right here is we wind up having these. This is going to be what's a secondary index. Okay, so it's not it's a non-clustering index. So what basically we have, and it's dense here, right? So we have all the search key values represented here, and then what these point to is these point to basically these buckets, and these buckets then have pointers to all the blocks that contain value. So we have the biology bucket is right here. Here's the biology bucket, and it points to this block here. So then if you look in that block, you'll find a biology. The comp sci bucket is going to be this one right here, and it points off to 3 separate blocks. All right, so that block and then that block. Okay, so what happens when you have these secondary indexes is you have some kind of representation that is at the bottom of the index, which what it basically does it points to, it collects all the things for that index, that search key value, and then it points off to the it forms a pointer to the actual records well, a pointer to the blocks that contain records with that search key value. There's other ways of doing this, and we'll get to these. So there's another way of doing this, which is basically instead of having pointers here, what you would want to have is you want to actually have you would maintain a primary index that would basically be clustered, a clustering index. It could be sparse, it doesn't matter. Like you can basically have this index here. Let's assume we just have this index here. What you can do instead here, instead of having all these pointers, you can simply have the value of the IDs here. So basically for biology, we just have the value of 76766, okay? And then what happens is that once you locate those, then you do another search using the primary index. So then you use this here, and then you'll find crick that way. All right, so that's actually an easier way to implement it in a lot of ways, because then you don't have to maintain these. You don't have to maintain, you have to maintain this index here. And then in this index here, you don't have to maintain pointers to blocks, because that's going to be taken care of when you do the second search on, the next search to actually get the values out. Okay, so that's the way secondary indexes work. Now, if you look at secondary indexes, you just might kind of notice here that this could be kind of problematic if you're going to have to do a lot of, I mean, in the worst case, if you have 10 people that are in computer science, you're going to have to bring in 10 separate blocks. Okay, so a lot of times secondary indexes, and those blocks might be a long ways away from each other. So secondary indexes do suffer quite a bit in terms of, they're not near as good as these primary indexes. But with SSDs, as we'll see later, this is actually getting a little bit better. So secondary indexes, because we don't have all random access is poorly performing as it is with disk random access in SSDs. So secondary indexes will become they'll become more plausible in terms of being useful for query processing. Okay, but they still are useful. So, all right. Anyways, these are, before we go into B+ trees, let's just think some common sense things here. Even with secondary indexes, let's say they give you some advantage. Primary indexes always give you some, big advantage. Just kind of the absurdity of saying, why don't we just build indexes for everything? All right, for all attributes, and just have a ton of indexes. Okay, so the problem with that is it's just a clear thing, that is that then you have to maintain them. So every time if you have updates to the database, then you're gonna have to update all those indexes, and that can make performance suffer. So there's a trade-off. There's a natural trade-off between the cost of updates and maintaining indexes versus the speedups you get for having a lot of different indexes. There's also another problem that happens with the query processing, and that is if you have too many choices in terms of different strategies of pursuing the indexing, that can confuse the query processor because it has to consider more. All right, so building more and more indexes is not always a great idea. All right, there's some kind of, that's why it becomes kind of an optimization problem, because you got to build just the right number of indexes over just the right attributes. Okay. All right, so the indexes. Okay, so there's really only one. Well, there's a lot of indexes, but there's this kind of one major index algorithm or strategy. It's been around for a long time. It's called the B+ tree, and this is kind of the dominant way you do indexing in databases. So we're going to cover it. Let's see. We're looking for time. I know I should. I'm going to fetch my coffee at one point because it's. I don't hear it yet. It has. I don't think it's boiled over yet. All right. Okay. So let's just review binary search trees. I'm going to do this very quickly. So I assume everybody's familiar with binary search trees. Yeah. So you basically just kind of keep things in alphabetical order as you add them in. The problem, of course, is that there's no guarantee based on how they come in. You can get like a linear. You can get like a kind of a degenerate case where if you insert them in alphabetical order, you'll get just a linear linked list. So the depth will be 12 in this case. The height will be 12. I'll call it the height will be 12. All right. So, and there's also a lot of pointer following, and also the fact that it's just binary. That's not going to get us very far. So the B+ tree is kind of a generalization of that in many ways, but it does something else where it basically keeps it so that it stipulates that it has to stay balanced. So the length from the root to the leaf in a B+ tree is always the same, no matter what. Okay, it's always the same. All the records are stored in the leaves. Okay, and so actually, as it turns out, that data file itself, those blocks that represent the data file itself, those actually wind up being the leaves of a B+ tree. Okay, so keep that in mind. The actual data structure itself, the data file with all the records, they're the leaves of the tree, of the B+ tree. All right. So the internal vertices are the index. All right. So that's just kind of definitional. So the actual index, the B+ tree is the total file, the whole everything. The index though is just the internal vertices in the B+ tree. Right. The advantage is that the fields are typically much smaller. Yeah, this is maybe not so relevant to say because this is based on a discussion that was based on there's something a little simpler called a B tree, but that's not this. Don't even worry about that first point. This implies the fan out. So basically, the index nodes, the index vertices, are going to not have so much in them. So they're going to have extreme fan out. I mean, they're going to have like fan out of like 120 or something like that. I mean, it's just going to be extreme amount of fan out, and that means that I mean, I don't know what's just intuitively what's 120 raised to the 7th. I mean, that's a big number. It's a big number, and that's how many records this thing can have. So, are you gonna ever have a B+ tree that's 7 deep or 7? The height being 7? Nah, I don't know. That would be a big database. All right. So the length, the distance to reach something would be in that case exactly 7 to follow the index. All right. Yeah, so they're rather bushy, so they don't go very deep, which is good. The leaf vertices, then we're going to see that we're going to string up the leaves, just like the regular data file. We're going to string up the leaf vertices. It's only in a primary index. We're going to string them up so we can have this sequential processing, and we can, well, it should be clear here. So here's an example of one of these B+ trees. This one right here. We say is a B+ tree of order 9, 4. So 9 is the number of pointers that are inside the internal vertices, and 4 is the number of records or the blocking factor. How many records can we shove in a block? Right. So these are blocks. Each of these are a block, right? And there's a lot more data than just that in the block. So it's like 40, and then let's say there's a whole bunch of data associated with that. Those are the blocks. So this is showing an order 9, 4. So the values which are stored okay, so in this case here, the values which are stored in the index here are just the possible keys. So like right here, we have, like if it's 39 or less, it'll go down to here, but 36 is not being stored anywhere in here. Thus this index, because here's our index, is a sparse index, right? It's a sparse index, okay? So the green vertices up here are the index, and the whole thing is the B plus tree, and there's the data file right there. There's the data file right here. And as we'll see, that we're gonna string pointers here to these block pointers to allow for sequential processing. Okay, no questions? Any questions, just put them in the chat. Okay, this is kind of just saying the obvious. That is that if you want to go and you search for or insert a value, basically, like if we're looking for 39 here, we'll go 39 or less, right? So 35, is 39 less than 35? No. So then we'll go here, boink. All right, now we come here. Is 39 less than or equal to 39? Yes. Okay, so we go here. So that's how it's less than or equal to. Then we follow it. All right, so now the thing is that these B plus trees have some conditions on them, and the conditions are they have to be half full, with one exception. And that one exception is always the root. The root can have just one search key value. Okay, it can also, the root can be completely full, but it can have one. So it's not, the root is exempted from the half full rule, right? But by doing that, these other ones are not. And by doing that, we maintain the balance. That's the invariant that maintains the balance. Is that these always, they can never go under half full, nor can any of the blocks for the file, I would say the record blocks, the blocks containing the data records, those can also not go under half full. And half full has a very specific definition here, and that is to take the number of pointers minus 1 and divide by 2, and then you floor that. That gives you the minimum number of search key values in an internal or an index node, index vertex. And then right here you take the ceiling of the number of basically the blocking factor, the number of blocks that could be in there, divide by 2, and then you seal that, and that gives you in this case it'll give you 2. And because 4 divided by 2 is going to be equal to, and seal that as 2, that will give you the number of records that have to be in a data block, all right, in the block in the actual data file. All right, so those have to be maintained. So under inserts and deletes, you have to maintain those conditions. All right, so here's an example of an insertion. So if you do an insertion here, we're going to insert 20 in here. And when we do that, okay, so here's the initial one. We're going to insert 20. All right, it's going to sit there. It's going to shove 20 in here, and it's going to make a change to the index here. It's going to basically change this from 20 to 19. So there's a strategy that it adopted here just to kind of shove this thing in there. All right, so the exact algorithms here of how this is done, the exact strategies of how this is done are highly idiosyncratic. So I don't remember I remember hearing it, but I don't remember the number exactly. But B plus trees are used by PostgreSQL, but apparently there are like 7 or 8 or maybe even more individual implementations of B plus trees inside the code base of PostgreSQL. And they all do things in a slightly different way. It's like we're told in software engineering, oh, you're supposed to make a generalized module, and then it gets parameterized by different subsystems, so they use they don't do it that way. They just rewrite the thing. It's completely it's duplicated code, because these are very fiddly things. You have to kind of fiddle it down and kind of make it so that it's behaving right. So one of the things you don't want to have happen. So in B plus trees, I mean, there's a lot of different ways, places where they get used inside the system. This is an example of an insertion here, and then you have issues of like an insertion into this right here. So this is problematic. When you do an insertion here, you're going to have to grow to maintain the invariant. You're going to have to grow the height of the tree. All right. So what a lot of these systems do not want to have happen, especially if there's a lot of that's expensive. That's unfortunately an expensive operation that has to happen to maintain the index. So what you don't want to have, you want to have some kind of momentum in the actual implementation strategy of the B plus tree. So you don't want it. The last thing you want is to have a B plus tree that's almost required to grow another level, and you add something into it, and it goes to the next level, and then you take something away, and it shrinks back to the earlier level. That's bad, bad, bad. If it thrashes kind of doing that, you want to have something where once you kind of go over that, then it's like it's more reluctant to have underfills, or it uses more strategies to cope with underfills. So when you finally have you have to overfill. So there's a lot of tricky stuff that goes on with implementation to get the exact performance you want, and thus the implementations get duplicated around the system's code base. All right, so there is no correct way to say, oh, this is the definitive way in which you handle insertions and deletions. It's not like that. It all depends on kind of what you're trying to do with it. What's the mix going to be? All right, so going through all this, I mean, you can study these slides later, and you can see kind of just a little bit of get a little sense though of how these things are handled. But basically, what's happening is sometimes you're forced to grow the height of the tree. Sometimes you're forced by deletions to shrink the height of the tree. All right. Okay, so now we're going to do like a little bit of. All right, so here's the sequential access. So I was saying before, like how our data files earlier had. So remember how our data files had these block pointers. So now we've stuffed them in here, right? So in the leaves here, we have the leaves of the B+ tree, which is the data file. We have the pointers that will allow us to do sequential processing and go through. So if you want to say something like, give me all the records between 28 and 47, you come down here, you find 28, great. And all you do then is just go forward here until you get to, okay, now we've gotten up to 47, right? So that's just like wank down to there and then sequential across, right? So that allows us to have these kind of range queries or sequential processing in general. All right. Okay, yeah. So, and then there's also, you can do back pointers. All right, so let's do a little bit of just kind of some notebook calculations here about how big these things get. Let's watch here. All right, so here's some assumptions, and then we're going to just do some quick kind of calculation about what's going to happen with we're going to kind of start considering how big is this B+ tree going to be, and more specifically how to do basically key-based access. How many blocks do we have to bring in? So so remember, this is a block, right? And this is a block. Oh, one second. This is a block, and that's a block. So if we want to say, like, how many blocks, let's say memory is completely clean. There's nothing in memory. Okay, let's say let's say the root node is in memory. Jesus, okay. So we have this block already is in memory. The block that has 35 is already in memory. And then we want to get access to 32. Well, we're going to then bring in this block. That's one block. So we had one block in memory already. Now we're bringing in another block, and then we come in here and we're going to bring in that block. So we bring in 2 blocks, right? I mean, more realistically, you will have all the blocks of the index in memory. They all sit in memory. Okay, fine. And then you just have to worry about bringing in just bringing in the data blocks. All right. So, so when we talk about the height of the tree, that's going to give us the number of blocks to just do kind of access, keep valued access is always going to be basically the depth or the height of the tree. Right? Depth is the height is 1 plus the depth. All right. So maximum depth. So that's going to be so we want to keep that. We want to have the depth low, right? Okay. So this is the depth of the index. But anyways, let's just run an example here and see. Okay, let's say we have the why does it say page size? It should say block size. That's annoying. How did that happen? I don't understand how that happened. I changed. I want to say block size. I don't want to talk about pages at all. But page and block are synonymous. It's just that a block is on disk and a page is in memory. But I like just to kind of run them together and say a block's in memory too. So anyways, but all right. So the block size or the page size is 2K. Record size, that's the size of each record. The pointer size is 4 bytes. This is the internal pointer to the for the internal vertices. the bytes per internal key are 16 bytes. The total number of records are 1 million. So we're going to have 1 million records we want to store. And then the total bytes per sequential pointers and leaves is 8. So there's the front pointer and the back pointer. So all the pointers are going to be 32 bit pointers. So we have uniform pointer size. All right. So anyways, you just do the arithmetic here. Say what's the number or the order? How many internal vertices can we have? Well, it would be n times the pointer size. But n minus 1 because times the key size, and that has to be under the page size. So in this case, if you work that out, you do argmax on n, you'll get, and then, well, this is floor, but a modern way to say this would be argmax. You get 103. So we can have 103 pointers inside of an internal vertex. All right, and then the maximum number of records. So the blocking factor would be basically, you're going to have the pointer, that pointer size. So the number of records, max records here, is we're going to do an argmax over argmax, is okay, the number of records, and then plus the pointer size, which is going to be 8 here. So just do the arithmetic and you get 15. So we can put, the blocking factor is 15. We can put 15 records in a block. All right, so that's a kind of a halfway realistic example. So now the question would be this. Under that example, we've got 1 million records we've got to store. What is the minimum height or minimum depth of the B plus tree? Okay, what's the minimum depth of the B plus tree? If we just brute force it, you just kind of count them up here. You're going to brute force it. We're going to find out that, well, if you get to this point here, this is the minimum. So what we're doing is we're basically making an assumption of minimum density. So we're making an assumption that everything is kind of half full, right? So everything's kind of teetering on the brink of requiring to go back one step in height or depth. Then what we have, making those assumptions, and of course the number in the root is 1, right? So it's the case where the root is only got 1 search value, so that would tend to maximize the height. If you just kind of grind this thing through here, you'll find that the maximum depth in terms of like the depth of the index is going to be, well, it couldn't be here because if it was this deep, if it was 3, then it would have to have a minimum of 2,249,000, et cetera, records. But we only have 1 million records. So that's a no-go. So it has to be of depth 2 of the index, but then that's just the index, and then what comes on later is the data file record. So we always have to add +1 there. So basically the maximum depth of the B plus tree then would be 3, because there's the extra one for the actual data file. So we have to count the leaves as a level. All right, so we get to 2 here, and then we have to add 1 more for the leaf. So it's 3. All right, that's the record right there. So if we do this more kind of intelligently and not brute force it, because this is kind of nasty, we do it more intelligently here. What we get is these are the parameters. M is the number of keys in the root. Q is the number of keys in the internal vertices other than the root. R is the number of records in a leaf vertex. That's leaf vertex is just another way of saying the data file. And then this is the depth from the root to the leaf. Okay, so basically what we have here then is we're going to say that it's, I mean, these are just kind of made up examples. This is kind of a made up kind of structure here because it's never going to happen in practice. You're going to have exactly that kind of balance. But we call this basically an MQRD uniform tree. So, okay, so under those assumptions there, then you do the mathematics. It's okay, here's the brute force. You can grind it out here. But if you do the mathematics and you solve for D, I'm not going to ask you guys to actually be able to rederive this, but you should be able to. It's like, logs and stuff. You get basically that it's going to be in agreement with with our brute force calculation, because we're going to basically say, oh, well, the minimum height tree we can have is height 3.7. The maximum height tree we can have is stretching it out as much as possible is going to be 3.79, but that's not quite 4. So no, it's going to come back to 3. All right. So that's that agrees with our brute force method. Okay. So this just kind of confirms the this analytic. And so what's interesting in this particular case, if we do the minimum, so this is when we're going to squish it down as much as possible. We're going to fill up the root to the max, and we're going to fill up all the internals to the max as well. Right. So we're going to really squash this thing down. And so what's interesting in this particular case with a million records is that if we go through the math, in that as well, we're going to find out that's also going to be the depth of 3. So they're the same. So no matter what, it's going to be 3 in this case here. So there's a spot where with the number of tuples basically are going to be like, it's not going to alter the height of the tree, right? It's in a bound that it's going to always be the same height of the tree. It's just going to kind of shift things around. And that might be kind of something nice to know, nice to calculate. I'm not sure if these particular equations were built into some of these things that try to do predictive. Well, if you know, again, the momentum of like lots of updates are coming in, then it's one thing. And then if you know that you're going to be getting a mixed update, you might want to put yourself in a band. Or you might behave differently if you know you're in a band where the height shouldn't go either way, so that you won't have to do the expensive adding or taking away of a level in a B+ tree. All right, so that was kind of how B+ trees operate, and these are what are absolutely used in PostgreSQL, SQL, MySQL. So they're definitely what's used. Again, I think I talked about this a little bit. The secondary index for B+ trees. So all these are just primary. These are all for all the considerations for primary indexes, B+ tree indexes. Which, by the way, when you say primary key, you automatically get one of those for free. So the database usually will just create an index if you declare a primary key. So you get those kind of, it's a given. And then it will also cluster on the primary key. So a lot of times you'll get pretty good performance just right out of the box with a lot of databases because they do that. Records of a B+ tree, well, yeah, you can only have one attribute or one primary key you're ordering things on, or one strategy to cluster. All right, so you're going to you can do it. You can have multiple attributes. You can cluster on multiple attributes, but the thing is, you can only cluster on one thing, right? I mean, because there's the kind of physical, unless you want to duplicate the data, which you don't. All right. So, but a secondary index is going to be on something other than that. So when that gets built and done, then we're going to have these bucket files. We're going to have these. So instead of, it's going to be like one level of indirection where what it's actually going to point to is a bucket. And I think the easiest implementation probably would just be to have these bucket files have just the ID of the primary index, right? So at the bottom you have the ID of the primary index, and then you can just go out and follow that. All right. So yeah. All right. That's. I mean, we're not going to cover it today, but we're not going to cover it. Maybe we're not going to cover it next time either. But maybe if we get the time. But the way you actually get PostgreSQL to kind of do these things and to kind of build indexes, we're going to cover. But right now, I just want to keep it more kind of what these things are. There's something, this actually is not really inside of PostgreSQL yet. I mean, although I think there's some ambiguity about that. But this notion of a bitmap index. Okay, so let's just hypothetically say the following. Let's say, before I do this example here, let's say that we want to, we have gender. We want to build a B+ tree index on gender, male or female. Secondary index. That's kind of going to be a dumb. I mean, if we have we have 10 million people in Sweden, and I mean, even if we have more than 2 genders, I mean, it's not going to be that many. And so you're going to have this index where it's going to start out at the top, and it's going to basically say, okay, this male, female, and then all the other ones and all that, but there are not that many of them, and then it just stops. And then you just have these. I mean, the index isn't that deep. I mean, it's not that many search key values. So it's kind of like, well, why would you do that? And the answer is, well, you don't. So, all right. But then what if we had something like this? Like, let's take a look at this example here, where we have people's age, and we have their gender. What it turns out that what we're really querying for are kind of these bucketed age brackets, 0 to 19, 20 to 39, 40 to 59, and then, so that's actually what we're going to wind up querying on those. I mean, we could build a secondary index on age, but all right, that might be kind of but we'll see. We'll think about the performance differences here. Well, what this bitmap here shows that we have just for each ID, it's as long as the number of records there are, we could build just a bitmap index on gender and just have to be 1s and 0s or other codings. That is just exactly as long as the number of tuples we have. And then we can also have one for these people, these age. And what this allows us to do, if we have those indexes, what we can do is we can say something like, well, if we want to get this query here answered, what is this? Where the female, okay, so that means that gender is going to be, I guess, 1. Okay, so sex equals 1. And then, okay, 60 to 75 equals 1. All right, so what that gives us the opportunity to possibly do is to do a AND with this vector of bits and that vector of bits. And it looks like that's a 1 and that's a 1. So that should be part of the answer. That's a 1 and that's a 1. So that should be part of the answer. And that should be it. So you're going to do these kind of bit operations to kind of to solve for those conditions. And that might be quite a speed up. And the thing is, this actually gets used a lot in this OLAP use case. So the OLAP use case uses this quite a bit. Or uses bitmap indexes. All right, so it shows a little bit more what you can do with, so like, yeah, standard hardware for bit manipulation, etc. So you can compress this even further and have an encoding here where you have 3 bits that signify. If you want to get the bitmaps a little bit smaller, that take up less space. The thing to also remember about bitmaps is you can use a lot of clever strategies, like you can do run length encoding. So let's say that we had a bitmap where, all right, well, it was very rare that somebody would be, that you'd have a 1 for that. You'd have like 1 followed by 10,000 zeros, followed by 2 1s, followed by 30,000 zeros, followed by 1 more. All right, you can compress that, dramatically compress that bitmap down into something that's run length encoding. It says basically run for 10, do a 1, now run for 10,000, so 1 plus T2,000 plus 10,000, and then implicitly 1, and then plus 1 plus 30,000 or something, and that is an extreme compression of that giant bitmap. All right, so you can get you can get these giant compressions when you have kind of rare values in the bitmap, like rare. It's rare that there's a 1. All right, and that generalizes to everything else too, not just 1s. But it could be other encodings. It doesn't have to be a bitmap. It can just be like a value map or something. So, anyways, there's a lot of potential there to get significant speed ups. All right, so let's see. What are we looking for in time here? All right, I think I can do this. All right, so hashing. All right, so you can call for hashing in a lot of databases. You can say build a hash index, but it's not. I mean, it's not really, doesn't really give you that much actually, if you think about it. So I mean, it doesn't. I mean, how many blocks are you really going to, I mean, it's like 2 blocks to get to, I mean, you know, you get real cases where you have a database where it's like, okay, let's say we have most of the indexes already in memory and we're going to do kind of access to like particular values. So we have to kind of do a couple, we have to kind of follow a little bit through the B+ tree, but we can at least do sequential processing through the B+ tree also. We lose that, or especially range queries, we lose them if we do hashing. Hashing might be a little quicker, but it's not really very generalized. So people hash indexes, no, probably not. But you're using a lot of hash strategies like in hash join. So this kind of stuff will then apply when we're talking about like doing a join. When we talk about query processing. So a lot of hashes are still being built inside a database, and they use this strategy as well. It's sensible hashing. So it's a good structure to have, but it's not really used for to build indexes over the actual data. All right. But anyways, okay, let's see here. So what do we have here? So how does this work? All right. Extensible hashing. So the idea is basically this, is that we have a hashing function, right? It's supposed to be a pretty balanced hashing function, which takes in a key and it plops out a bit string, basically. All right, and it's going to basically do this. It's going to basically, we have 2 different things here. We have the actual directory, which is what's going to be extending. It's going to be getting bigger. And then we have buckets. We have bucket blocks or bucket pages. All right, so these buckets, really bucket blocks, I would say. Yeah, anyways, these buckets then are going to contain the actual records. All right, so let's just do this little example here. So we have a 3-bit is the directory here, and then we have a 13 bits is the hash address, and it calculates for 13 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, anyways, so basically what we do here is we calculate the hash function, we get this out, so we put a key in, we get that out, then this is the 101, so that's right here, so he must be the one who's down inside of inside this bucket here. But we have a leaf address that's associated with that record. So we don't want to recalculate it. We just have it there, okay? So we have a record in here with an associated leaf address, right? So this is using the first 3 bits, but well, okay, fine. It uses the first 3 bits. And it looks like, actually it looks in this case, well, in this particular case here, if you just have starting out with a 1, those all point down to this bucket here. So there's only really one record here that actually got leading 1 on its hash value, all right? That's the case in this case. All right, so now the depth of the index is the number of bits in the hash value, which the depth of an index is the number of bits of the hash value which is used as the index value. So it's basically 3 here. That's the depth. This is just a little bit. I'll get rid of this. This is not. It's really more just intuitive. For some reason, we have a blocking factor, so only a certain number of records can fit into a bucket. And for some reason, we were required to split to get down to here. So let's see if we have a better example here. All right. So suppose that the bucket which is shared by, all right. So the bucket that's shared by, okay, these guys right here, 0, 0, they map to this bucket here, right? So we've had records that have been plopped into that bucket. Now let's say we plop another record in that bucket, but it actually makes it so that they can't all fit in the bucket. So we got to split the bucket. Right. So what we do then is very simple. All we do is we just split the bucket, and that gives us a lot more space. And then the way we place things in the new bucket. So we have a bucket. We split the bucket. Now we have to place stuff inside that what's already in that bucket into the new buckets. So all we do is we simply look at the leaf address for those, and then based on that, we will take up another bit and determine which ones they go into. So we'll most likely get somewhat an even split, and then we'll feed these up. We'll create 2 buckets there, and then notice what happens here is now the pointers in this bucket, the pointers from this directory here, now point to these individual buckets. All right, so that's how that happens. So the only thing is that what might happen though, eventually, is you get to a point where you have to actually grow the full size of the directory. So you have to go up to 4. The depth of 4 from the depth of 3, and then when you do that, what's nice about that is you don't have to do very much. I mean, you have to do the operation on the actual directory. Yeah, sure, you have to kind of double the size of that thing, but you don't have to go and change anything around, in the buckets other than the one that got split. Right. That's the only one you need to do that with. Is to do any kind of pointer. Otherwise, you just kind of duplicate the pointers. Right? So it's a really nice, elegant little structure that does extensible hashing. Really kind of a cheap way of kind of building up building up hashes so that the hash is kind of minimal. The size that the hash maintains itself as kind of a minimal structure. So that's kind of nice. All right, so works best when insertion modifications are dominant for it. So when there's deletions, that's when it kind of gets a little bit bad. But usually you'll see in the query processing aspect, it's almost always just insertion as you're doing the processing of the queries. So the random access, yeah, it could be, because I mean, again, what's nice about it is that you just take the key value and you do one operation on it, and then you get the exact address of the bucket where the record is. So that is nice. You're skipping traversing things in the tree. So no searching is required, just computation of the key to address transformation, and then yeah, I mean, as you get larger memories, so that you can stick the whole index. I mean, once you can stick the whole B plus tree index in memory, then that really kind of vanishes. Sequential processing is hopeless. I mean, it's just terrible. There's really no range queries. I mean, and sequential processing. I mean, because the things that wound up in those buckets are just kind of really randomized. So that's a problem. Okay, yeah, we're not going to go that far today. So let's see here. Perfect. Yeah. So we've finished exactly on time. And how do we, okay, that was the question from before. So are there any questions? Are there any questions now? Okay then, so I think that will do it then. And then next time we're going to talk about query processing. And I'm not even sure if I'm going to take away the Alex incident. I mean, I'm just going to upload the file to the non-listed YouTube video. So, all right, well, if there's any last possibility for questions, please ask. Otherwise, we will see each other on Friday. And also, yeah, with projects, I'll stop the recording here, and then I'll talk a little bit about projects. One sec. Or actually, maybe I'll say it because other people might. Okay, projects. Yeah, so if you go to the content on Cambro, you can see there's 3 projects that have been accepted. I talked to a lot of people, and I think there's a lot of good projects, a lot of interesting projects that people are talking about. Yeah. So anyways, just touch base again on the projects. Again, the sooner we can get this discussions kind of concluded. I have some ideas about some applications now, which I think will be kind of cool. But we can just kind of, if people need an application, I have some ideas. But I think a lot of people had some good organic, the ideas that were inspired by their own curiosity and interests. So I think that's always good to follow those if you can. All right, good. All right, see you guys Friday. All right.